All right, good morning, everybody. Let's go with a couple of announcements. First, on Tuesday, we're going to have a quiz. We would have had it today if I'd thought of it earlier, but we'll definitely have it on Tuesday, so now you get some warning. Next Thursday, you're going to have the first assignment associated with Chapter 6. Chapter 6 is all about fluid momentum, and we'll begin talking about that today. So the first assignment's due on the 8th, so that's a week from today. And then you'll have the second part of the fluid momentum, the assignment due on Tuesday the 13th. Now, also on the 13th is going to be the second midterm exam, and I'll give you a lot more details about that as we move forward. But just to give you a broad overview, it's going to be covering chapters 4, 5, and 6. Now, the interesting thing about this exam is in the past, I gave students the challenge that if they took the exam without any equation sheet, then I'd give them like a small bonus. And some of them did it, and actually the people who used no equation sheet were better off than the ones who did use the equation sheet. And the reason why I gave them that challenge is that these are all relatively simple ideas in these three chapters. I mean, in chapter 4, you've got like what formulas you need to memorize, like Bernoulli's equation, Euler's equation, rotational flow, and maybe the equation for convective acceleration. Chapter 5, that one's pretty easy, Q equals VA. And then chapter 6, as you'll see, there's really just one formula at the heart of this chapter. So I'm not going to give you that same challenge, but I just mentioned it to make the point that there's lots of different problem types that were in the first exam, so many different formulas. But in the second exam, there were fewer number of concepts, but maybe the depth of them is getting a little bit more important. So begin to think about preparing for that test because it's coming up. All right, now before we start talking about fluid momentum, let's just revisit briefly the idea from yesterday's lab experiment. Yesterday I gave you the handout for the design of experiment assignment. And essentially, you're using the pipe rack to test the Hazen-Williams equation. And the handout, I gave you this version of the Hazen-Williams equation. If you look in the FE reference manual, that equation packet that you get to take into the FE exam with you, I guess more accurately, it's available as a searchable PDF when you take the FE exam. It has two forms of the Hazen-Williams equation. So the first form, which you've already seen, you're solving for velocity through a pipe in terms of a certain slope of the energy grade line. So S sub F is the head loss relative to the pipe length. The other form of the head loss of the Hazen-Williams equation solves for the unknown head loss when you have a given velocity, a given length, a given C sub H value, and so on. So just the broad strokes is what you're doing in this experiment is you're going to develop an experimentally derived average C sub H value. So you'll look at the 4 different pipes, and you'll have 3 different flow rates through each pipe. So of those 12 runs, what's the average C sub H value? So you'll determine that experimentally. And the reason why is that then I want you to put that average C sub H value into this form of the Hazen-Williams equation and predict the pressure change. And so kind of putting it back into this equation where we know the pressure change is the head loss times gamma. How does the observed pressure change compare to the predicted pressure change that Hazen-Williams says you should see? So you're testing how good is this equation at predicting head loss through a pipe. So the experiment that you need to design should have those two objectives, that two phases of the project, finding the C sub H value and then testing the Hazen-Williams equation. Does that make sense to everyone? Any questions about this? Yeah.
I know when we worked with water jams, you said that this was always the preferred equation to use.
It's actually the other one. So this is the one that we switch it from. It starts up the program in default. It starts with Hazen-Williams, and they choose it because it's accepted. It's a good equation, and it's easy to solve computationally. But then since we are really hardcore, we always switch it to Darcy-Weisbach because that's what hardcore people do. It's the more sophisticated equation that we'll learn next semester in 331. It's a real fancy equation, and the computer can handle it, so we bump it up a notch. But yeah, I'm glad that you remembered that this is built into water gems as one of the options. Is there any other questions about that lab assignment? When can you start doing your experiment? Tuesday, 8 a.m. And you'll have until 5 p.m. on Friday of next week. Okay, well, let me know if you have any questions, because this is an important project, and I want everyone to do well. We're going to watch a brief video that illustrates some principles of fluid momentum. It is two really cool things, a wingsuit and jet boots, put together in one beautiful combination. Yeah. Yeah, he beat the odds that day. But that's the last video I've seen posted. So I don't know if there's a follow-up story to that. I mean, I've searched and searched, but that guy like fell off the face of the earth eventually. Yeah. With big fires on each foot and a wingsuit and a parachute. So, I mean, it's an inherently dangerous pursuit, but he seemed to enjoy it at the end there. So, I don't know. That's Finland. Yeah. So, let's do a calculation exercise here using a couple of data points as just an illustration. So, some of the specs that are given in the accompanying information that I found was that each one of those boots yields 16 kilograms of thrust, and to prime it, like to heat up the jet and to get it spinning before they start injecting the kerosene, it was a mixture of butane and propane. And then once it's actually burning, it was half a liter per minute per jet. And so you saw he's kind of waddling around with the kerosene in the enema bladders, as you pointed out, and then jumped from about 7,000 feet. And what he said, the accent's a little tough, is that he was able to maintain altitude, and he was actually going to try and climb a little bit to gain some additional height, but then there was a stall, because I guess the wingsuits aren't really necessarily designed to generate a lot of lift. They're supposed to give you a little bit of forward motion as you fall downward. And I think what I read is the typical glide path is that you'll move forward 1 foot for every 3 feet of drop. And so that's considered like a good forward movement with those wingsuits, but he was, maybe it's 3 horizontal for every 1 vertical. In any case, he was trying to go horizontal with it, and it stalled. So kind of an interesting application of momentum, because to get that forward movement, there has to be some mass flowing out of the control volume. And we'll draw a sketch of the wing boots and talk about the momentum flow out. But this is all derived from Newton's second law, so that the imbalance in forces will cause an acceleration on a mass. And so in the case of the example that we were just watching, the mass is his body, the equipment that he has with him, and then the imbalance of forces was the jet boots, and what it caused was a forward acceleration. Now, let's substitute in a definition of acceleration. So remember, local acceleration is a change in velocity with respect to time. So if we substitute, instead of a, we have dv dt, so change in velocity in change of time, and we combine the mass and the velocity inside together. That is what we'll define as momentum. It's mass times velocity. Now, this is applicable for a system of particles. Instead of just a single particle like a person with a jet boot on, we could apply these same ideas to a stream of water. And remember that a system is a continually connected mass of fluid particles, and the number of those particles stays constant, but its location over time can change. So we can apply these ideas of momentum to the Reynolds transport theorem. Remember that some properties are carried through and can be balanced along with the fluid. And momentum is one of those mass-dependent properties where the momentum can be accumulated inside of a control volume, and the momentum can pass through control surfaces. And so how this is different from the Reynolds transport theorem that we've seen before is in the past when we were doing Reynolds transport theorem, we had, let's just use the flow out, in and out through the control surfaces as an example. In the past, we had some differential area dA that the stream was passing through. That was the cross-sectional area. V is velocity, the density, and so those three terms together, the density, the velocity, and the area through which it's flowing, was the mass flow rate m dot. But what we're saying is now let's keep track of not just the mass flow through a control surface. So if we have a control surface and we have some fluid jet going in and some fluid jet coming out, let's do more than just keep track of the mass flow rate, but let's also multiply the velocity of that jet as it goes in and out. So each one of the streams will have a mass flow rate in, will have a mass flow rate out, and we'll also be keeping track of the velocity in and the velocity out, because the product of those two things, the mass flow rate and the velocity, is together the momentum. So what this Reynolds transport theorem is saying is that we can apply this mass balance idea, and inside of the control volume there can be an accumulation of momentum. If this jet that's coming in and out, for instance, is hitting some sort of an impeller, then when the stream first starts, it could cause that impeller to start spinning. Well, maybe it's attached to a flywheel that retains the momentum, and then even if you switched off the jet, that flywheel would continue to spin. And so that's an example of how inside of the control volume, momentum can be stored. And so the difference between the two is the change of momentum of the system over time. Now, combining that with Newton's second law, what we're saying is that the imbalance of forces that's applied to a system is what accounts for the difference between the momentum flow in and out and the accumulation within the system. Now, it's a pretty specialized case, this idea of momentum accumulation inside the control volume. We don't apply it very often. Mechanical engineers maybe would apply momentum accumulation for like hybrid cars or some specialized applications, but just for simplicity's sake, let's start with the assumption that we don't have accumulation of momentum in the control volume. We'll start just by looking at the in versus the out. And so with respect to time, we'll assume that conditions in the control volume are constant, and so there's no momentum accumulation. That simplifies the Reynolds transport theorem and allows us to say that the structural parts are stationary, there's no momentum accumulation, and so it's just a matter of the sum of forces inside of the control volume, the sum of the forces required to hold the system steady can be determined by looking at the change of mass flow in and out, where you're also keeping track of the velocity in and out. So before we move away from the assumption of no momentum accumulation, look at what a flywheel looks like and how it works. All right, so that gives you a pretty good idea of how momentum can be transformed into energy and vice versa. This is the form of the momentum equation that we'll actually use in problem solving, though. And the way to say it in words, on the left-hand side of the equation, this sum of the forces, it's the sum of the external forces required to hold the system steady. That's what this is actually going to be calculating. And so the sum of the forces required to hold the system steady is the sum of the forces going in and out through the control surface. And the velocity times the mass flow rate is what we'll use in practical terms. Now, the forces that we're talking about here on the left side of this equation, forces can be divided up into a couple of different categories. There's the body forces, which act at a distance without physical contact, and that's not what we're talking about in fluid momentum applications. The fluid forces that we're talking about is when a water jet actually makes contact with some other surface and applies a force because there is that physical contact. And so we're talking about surface forces. We're not talking about, in this equation, forces like gravitational, electrostatic, or magnetic. So we transform the Reynolds transport theorem and this Newton's second law into this practical version of the momentum equation when we look at applying it in a certain direction. So the primary difference between the two here is that we are able to apply this in any direction we choose, but we have to do it in one direction at a time. So in the x direction, what this means is that the sum of the forces required to hold a system steady can be calculated by looking at the mass flow out and the velocity out through a control surface minus the mass flow rate in times the velocity in through a control surface, and both of those are in the x direction. So on the whiteboard here, I drew a control surface, and there's some important sign conventions that we have to be aware of when we use this equation. And the first thing I'll mention to you is that it's out minus in. So out minus in, if you switch those, then you'll get the wrong answer because there's a directionality assumed with the forces, for instance, that positive, when we're working in the x direction, positive is assumed to be to the right. And so you have to, first of all, have the out minus in. And the other thing to pay attention to is that although mass flow rate is a scalar, meaning it only has magnitude, velocity is a vector, so it has magnitude and direction. So if you're keeping track of some stream of water, like a jet, and it's going in the positive x direction, then the value you'd put in here for velocity is positive. But if the jet is going to the left, and your sign convention is that to the right is positive, then you need to put a negative value in front of the magnitude of the velocity. You can also apply it in the y direction. So this shows the momentum equation for x. In the y direction, it's essentially the same process. It's just now that we find the component of the velocity that's in y and substitute it into the general form of the equation. So pay special attention to the sign convention. And so to the right is positive. In the y direction, we assume that up is positive. And now it's also important to, for each stream of flow, be sure to put it in as an in or an out. And this seems pretty easy, but let's practice it anyway. So here we have a control volume, and a stream is going in and a stream is going out. And our sign convention, remember, is to the right is positive and up is positive. So what this shows is that the velocity out is positive in x, and the velocity in the x direction is positive. So if we substitute it, if we had actual numbers there that we substituted into this momentum equation, then we would put a positive value for the magnitude of velocity out and a positive value for the magnitude of the velocity in. We can have multiple streams coming into a control volume. So what if there's two jets coming into a control volume, and that can just be like a black box of some sort, where inside of the black box are various veins or pipes that's redirecting the flow. So we have inside here something that's redirecting these two streams together, and the two jets exit that black box downward. So you can see two ins and one out. So this is showing that the velocity out is in the y direction downward. So whatever the magnitude of the velocity is, we need to put a minus sign when we substitute it into the force equation, into this momentum equation to solve for force. You can see that the velocity in is positive because it's to the right at 1, and at 2, since it's to the left, we'd put a negative sign in there. And this third one is where it gets a little bit tricky because these streams, these fluid momentum streams, can have both x and y components. So stream 1 is partly in the x direction and it's partly in the y direction. So, in which is it positive and in which is it negative? So what we could say is that the velocity in at 1, I guess let's sketch that up on the whiteboard using the same approach. Okay, so velocity in at 1 in the x direction. Is it positive or negative? The x component. It's positive, right, because it's to the right. Now, still on stream 1, what about velocity in at 1 in the y direction? Negative, right, because it's downward, vertical component is downward. All right, let's look at stream 2, which is also in. So velocity in at 2 in the x direction. Is that positive or negative in the x direction? Negative, good, because it's to the left. Velocity in for stream 2 in the y direction. Also negative because it's downward. And then the third stream, which is the out, so velocity out at 3 in the x direction. Positive because it's to the right. And velocity out at stream 3 in the y direction. Also positive because it's up. So you get the idea. That's how we apply the sign convention for these types of problems. And we'll have in these this chapter 6, you'll have control volumes that there can be 4, 5, 6 streams coming in from different directions, and it doesn't matter how many of them there are, you just keep adding them all together. That's why this summation term is here, is that you just find all of the momentum out in the x direction. And it can be one stream or it could be multiple streams, but you just combine all of them together while you're honoring the convention of to the right is positive, to the left is negative, and vertical, up is positive, down is negative. So here's a problem-solving approach that's suggested by the textbook. What it says is that the first step in problems like this is to find out what is going on, like where's the magic happening, and surround that system of interest with a control surface, and so that inside of it is the control volume contains where the momentum is either changing direction or where maybe a jet is impacting some sort of a container or a vane. So you find where the system of interest occurs. You apply governing equations. So the governing equations that can be used in problems like this might be having to do with changes in pressure due to changes in velocity. So then the governing equation you'd use is Bernoulli's equation. Sketch the forces that are required to hold the system steady and look to see if there is momentum accumulation possibility. I think in most cases we'll find in our problems that there isn't momentum accumulation. And then sketch the momentum flow vectors. Okay, so let me show you what that process looks like when it's actually applied to a simple momentum flow problem. So in this one, we have a little balloon on a nozzle, a balloon with a nozzle that is connected to a straw. So the idea of the straw and the string is so that the balloon goes in a single direction. You know that if you just let go of the balloon, then it's flying all over the place in random behavior. But here, the string and the straw that's connected to the balloon just means that it's only going in the x direction. So we're going to apply this momentum principle in the x direction. Now, what the problem statement tells us is the pressure inside the balloon. And they're using kind of unusual units that we haven't seen before. what they're saying is the pressure inside the balloon is 0.4 meters of water. Anybody have a guess on what that means? Instead of kilopascals, they're saying the pressure inside the balloon is 0.4 meters of water. Excuse me, what's that?
0.4 times 98 pounds.
Exactly right. That's how you'd find the pressure. So they're saying the pressure inside the balloon is the same pressure that you'd see at a depth of 0.4 meters of water. So sometimes we use a depth of water as an equivalent pressure. So let me sketch, first of all, on the whiteboard here, what's going on with this balloon. We've got the balloon, and it has a hole with this nozzle, and air is coming out, a jet of air is coming out, and inside the center of the balloon, here at 1, the pressure at 1 is 0.40 meters of H2O. So we can convert that to pressure in units that we're more familiar with by saying 0.40 meters of H2O times 9810 newtons per meter cubed. And that will give us a pressure at 1 of 3924 newtons per meter squared. Okay, so that's what the pressure is inside the balloon. And by the way, that's a gauge pressure. So that's relative to the pressure surrounding the balloon, because we've got atmospheric air on all sides surrounding the balloon. Now, the other thing, just like taking care of some of the preliminaries early on, they've specified that the diameter of this nozzle is 1 centimeter, 1.0 centimeters. By the way, does anybody have a marker? This thing seems to be losing its juice. I usually try and bring a couple, but fell down on the job today. Thank you. All right, so we've got 1 centimeter diameter here for the opening. From that, we can calculate the cross-sectional area. It never hurts to calculate a cross-sectional area when you're given a diameter, because 9 times out of 10 you'll use it. So area is going to be pi d squared, 0.01 meters squared divided by 4. So the area is 7.854 times 10 to the minus 5th meters squared. Okay, so that's the cross-sectional area of the opening. We also have, just as a matter of givens, the density of air. So the density of air is 1.2 kilograms per cubic meter. Okay, so let's do some sketches here. We can put a control surface that encloses the balloon, and the important control surface where the stream is coming out right here, what we want to know is what force is required to hold this balloon steady because of the stream of mass that's coming out of the balloon. So the unknown here is what force is required to hold the system steady. So Bernoulli's equation is what we can use to find the velocity of the jet that's coming out. So you can see here the jet of air that's coming out of the balloon. I've labeled that with 2. So this is kind of similar to how the orifice equation is developed, is by applying Bernoulli's between 2 locations. In this case, instead of doing it in a tank where location 1 is at the top of the water, we're going to do it where we know the pressure at location 1 and the elevations are the same. So let's just write Bernoulli's here. So Bernoulli's equation in terms of pressure is P1 plus gamma Z1 plus the density times velocity 1 squared divided by 2 is equal to P2 plus gamma Z2 plus density V2 squared divided by 2. So that's Bernoulli's equation. And what we can do is we can cross out both of the elevation terms because we're applying it between 1 and 2 that are on the same vertical plane. So we cancel out the Z1 and Z2. Now, inside the balloon, at 1, there's no velocity. This balloon is contracting, and here at the center, the air isn't moving anywhere. I mean, there is air that's going in towards the outlet there, but we're going to say that in the center of the balloon, the air velocity is 0, so I'm going to cancel out the V1 term as well. And finally, at 2, the air pressure is 0. So P2 is 0. So we can cancel that out. And all right, so what we can do is rearrange Bernoulli's equation. What we'll have is P1 is equal to the density V2 squared divided by 2. And so rearranging that yields a way for us to calculate the velocity at 2. And that's what we want because that's the velocity of this jet that's coming out of the balloon. So V2 is 2 times the pressure at 1 divided by the density, and we take the square root. Okay, so let's substitute in the actual numbers that we've got. It's going to be 2 times this pressure at 1, which we calculated in the preliminaries, is 39.24 newtons per meter squared, and divided by the density of the air, which is given as 1.2 kilograms per cubic meter, and that is all to the 1/2 power. Okay, so if we've got that much pressure, it's going to be forcing the air through that little opening at a velocity of 80.87 meters per second. So that's the velocity that we get. That's the gas exit velocity. So the question is, now that we know how quickly that jet of air is going out, how hard do we have to press on the balloon to hold the system steady so that it doesn't begin to accelerate to the right? Now this is where we use the momentum equation. So here for momentum, we've got the sum of the forces in the x direction is going to be the flow through the control surfaces out. So the mass flow rate out, the velocity out in the x direction, minus the flow through the control surfaces, where we've got mass flow rate in, velocity in the x direction. All right, so let's look at the control surface. And do we have any streams of mass coming in to the control surface? There's no in term, so we can cancel that out entirely. So what that tells us is that the force, the external force we have to apply to hold the system steady is going to be determined exclusively by the mass flow rate out. Okay, so the force required to hold the system steady in the x direction is going to be the mass flow rate out, the velocity out in x. There's only one stream, so here the summation of all the streams, it's just the one stream that we've got. So we already know the velocity. What about the mass flow rate? Okay, remember mass flow rate is density times area times velocity. Mass flow rate, is it a scalar or a vector? It's a scalar, so that means it only has magnitude. What are the units of mass flow rate? Do you remember what the units will be when we put it all together? Kilograms per second. So it's mass per time. Kilograms doesn't have direction. Time, I guess you could say time has a direction moving forward. But the point is that mass is a scalar. So sometimes students make a mistake because they see the v here, and if the velocity's to the left, then they'd put that negative value in this velocity. So don't make that same mistake. The velocity here has direction when it's just the velocity times the mass flow rate, but mass flow rate itself has to be a positive amount. So this jet is going to the left. And so later on, we're going to put the negative value in the this v, but don't put the negative value when you're calculating the mass flow rate. All right, so the mass flow rate then is going to be the density, 1.2 kilograms per cubic meter. The cross-sectional area that we got from the 1 centimeter diameter, so that cross-sectional area is 7.854 times 10 to the minus fifth meters squared. And then we are going to multiply it by 80.87 meters per second. All right, so can you do those calculations and tell me how many kilograms per second is flowing through that nozzle? Good, yeah, that's what I've got too. 7.62 times 10 to the minus third kilograms per second. And we've got it in our mind, yeah, mass flow rate is a scalar, so we're not going to put any negative sign there. Okay, so it is 7.62 times 10 to the minus third kilograms per second for the mass flow rate. And now for the velocity, we're looking, we see that the jet is to the left, and so that's minus, and the magnitude of the velocity is 80.87. So I'm going to put in here minus 8087 meters per second. Okay, what is a Newton? What's the units combination that gives us a Newton? Right, kilogram meter per second squared. That's a Newton. So what about here? We've got kilogram meter per second squared. So it works out. The magnitude of that force is negative 0.616 newtons. And the negative sign means that you have to apply the force to the left to hold the system steady. Now, like, what did your instincts tell you when you first started this problem? If you're holding on to a balloon and all the air is coming out that way, I mean, you kind of already know, without even putting the numbers in, you're going to have to push it this way to resist that flow. In the same way that, you know, when you hold on to a hose, you kind of know that the hose would push you backwards if it's a really big hose, and you have to kind of like lean into a little bit to resist the outward flow of all that mass. So this tells us the magnitude of the force required to hold the system steady. Now on problems like this, it's really important that you let me know that you understand the direction. And so I would write here in words, push to the left to hold system steady. So we've got a sketch, and it's showing that the direction of the force is to the left. I've got the minus sign here, and I know in my mind that sign convention is negative is to the left. And then here in text, I'm also re-emphasizing the force applied is to the left. Okay? So any questions about that? There's lots of different problems that use momentum principles. We're going to have a lab once you're done with design of experiment. We'll go into the lab, and there's some pretty fun equipment where we change the deflection angle for fluid jets, and we look at what forces are required to hold the system steady there. Okay. This is another kind of a interesting momentum application. Yeah. Sure.
On
yeah.
Tuesday, November.
Where it's drawn to the left, like all the forces were initially drawn to the left, and it came out negative.
Yeah. Good question, yeah. So you're wondering, like, the minus sign, if you always have your force assumed that the force is to the right, then you could say minus is telling you that it's actually to the left. You wouldn't want the double negative to give someone the wrong idea. So you could say that it depends on how you prefer to communicate the information. You can have the sketch show the actual direction, and then maybe the magnitude of the force, you only specify the amount and not the direction. So it's because we found a negative here, that doesn't mean that the force is actually to the right. It's just I kind of already knew that the force was going to be to the left. So I don't know if that clears it up, but to the right is positive, to the left is negative. Yeah, we'll practice that a few more times, and let's try and tighten up so that there's never any confusion, like the force direction arrows that are drawn. Thanks for asking about that, because I think I understand what you mean. All right, let's get this commercial out of the way. All right. I'll better pop. Okay, so here's some stats that I found for the Flyboard Air. The rider, 80 kilograms. The board and the fuel together has a mass of approximately 20 kilograms. And it's burning about 2 kilograms per minute of fuel. The fuel-air ratio, for every kilogram of fuel that's burned, then 3.5 kilograms of air is consumed. And so that means that if you use 1 kilogram of fuel, you're sending out through the bottom of the board 4.5 kilograms of mass. And that's important because it's not just the fuel that comes outside, out the bottom of the Flyboard Air. So we can use this momentum principle in the y direction to find out what's the mass flow rate of the exhaust and what jet velocity would have to be achieved in order to, under these assumptions, to hold the rider steady. So I think the best case scenario is if we do like a quick little sketch here. Here's the system, and a bunch of air is coming out, and that's what keeps it level. So let's draw a control surface. So we've got this stuff coming out, and there's a mass flow rate out, and there's some velocity out. You're going to get maximum thrust if there's not anything coming in. So if we assume that the mass flow rate in is 0, and that the velocity in is 0, that's how you can get the best case scenario. And if the total mass is 100 kilograms, then the sum of the forces in the y direction to maintain level flight is going to have to be equal to 100 kilograms and a gravity of 9.81 meters per second squared. So there has to be 981 newtons of force to keep this 100 kilogram rider plus equipment level. And you'd need even more force than that if you actually want to go up. If you want to be able to accelerate upwards, then you'd need more force than the 981. But let's just say how much is required to maintain level flight. Okay, so the mass flow rate of the exhaust that's coming out, the mass flow rate out is going to be 2 kilograms per minute, and in 1 minute there's 60 seconds, and then the mass flow rate has 4.5 kilograms of exhaust for every 1 kilogram of fuel, because the 2 kilograms per minute, it was 2 kilograms of fuel. So what's the mass flow rate of exhaust? Well, it turns out to be, under these assumptions, 0.15 kilograms of exhaust per second. So what we now can determine is what jet velocity has to be achieved, because the forces in the y direction should be the mass flow rate out, the velocity out in the y direction. So we can rearrange this and solve for the velocity out in the y direction is going to be the forces in the y direction divided by the mass flow rate out. So we have to have 981 newtons of force to hold the 100 kilograms level if gravity is 9.81, and the mass flow rate was only 0.15 kilograms per second of the exhaust. So that would mean that you'd need to have a velocity of 6540 meters per second. That's really, really high. And I mean, there's no escaping these physics. Either the way that you're going to have this thing levitate is by having a large mass flow rate or a large velocity or some combination of the two. You know, if you want to develop a force, like whether it's a flyboard air or a rocket, it has to be mass at a certain velocity to generate that. And so here, 6540 meters per second, what we're saying essentially is that the gas that's going out would be going 6.54 kilometers per second. And that seems probably unrealistically high to me, so maybe that flyboard air can't actually fly for the 10 minutes that this would maybe suggest, because it seems like the mass flow rate would have to be higher, since that jet velocity maybe isn't achievable. But that's just another illustration of how momentum applications can be used in a simple way where there's only a flow out and no flow in. There are three main types of problems that you're going to be solving in the homework. There are going to be problems that involve fluid jets, and so here's an image that kind of summarizes those types of problems. And so a problem like this would say, what's the tension in this cable? You know, find the tension in the cable. So what you'd have to do, you'd have to look at the jet here is a stream of concrete that's being sprayed into some container. And so you can visualize if that cable wasn't there, what would happen is a jet would be pushing that whole system to the right. And so the tension in the cable is the force required to hold the system steady, in other words. So that's one kind of problem type, is the fluid jet problems. Another problem type is vanes, where some sort of a plate will be deflecting the direction of a jet of water. And so then questions like this would be saying, like, what force is applied by the water to the plate? Or the equal and opposite reaction would maybe be, what force is the plate applying to the jet in order to cause this deflection? So that's the second type of problem that you'll be solving in Chapter 6. And then the third and most complicated problem type is nozzles. And nozzles are a little bit complex because, we'll get into the details of it, but you have to account for the pressure inside the pipe in addition to the momentum flow. So that's what makes this third type of problem a little bit tricky. All of them can be solved by the sum of the forces is the outflow minus the inflow. And the way to interpret this is the force required to hold the system steady. So like in the case of a vane problem, if the problem statement says find what force does the water apply to the vane, then that would be the opposite of the force applied by the vane to the water. So you kind of have to pay special attention to the text in the problem to determine whether it's asking for the force required to hold the system steady, or if it's asking what is the system's force applied to the jet. Okay. When we get together in class on Tuesday, we're going to begin with the quiz, and then we're going to start solving some of these examples to get more experience with momentum problems. That's all I have for you today. Let's just take one last look at these announcements here, peering into the future. Tuesday, quiz. Thursday, homework assignment. Then the following Tuesday, exam and homework assignment. So we've got a busy couple of weeks, but then the nice thing is, of course, we've got Thanksgiving in the medium term. So, all right, I'll see you next week.